This was the last slide in the previous class. Again, want to remind you, unless specified otherwise, all fields now onwards are Eulerian. So when I am talking about steady flow field, I am talking about an Eulerian flow field. So the definition of a steady flow field is if all these fields, velocity, pressure, density, temperature, do not change with time over a time interval gamma, then the flow field is called steady over that time interval. Mathematically, it will mean what I have here, partial derivatives, not the total derivatives, partial. That's the definition of steady flow field. It's possible that, for example, del rho del t is 0 and yet d rho dt will still be not 0. Possible. Definition of steady has to do with this. It doesn't care about this. In contrast, on steady flow field, if any of the quantities, what I have written here, has non-zero partial derivative with time at any x, even at 1x, if that is violated, it will become unsteady, or at any instant. Okay. This is just repetition, same thing. Let's focus here. A steady velocity field. Earlier I talked about a steady flow field. Now I am talking about a steady velocity field is one in which only this has to be 0, but at all location and at all time instants during that interval gamma. So it is possible that you have a steady velocity field, but yet the flow field may not be steady, right? Because for a flow field to be steady, all variables should be time independent, partial. Whether the velocity field is steady or not, it depends on the reference frame in context. What I'm trying to say is that if fluid is moving in this room and you are an observer sitting on ground, you find out that with respect to you, this is true. That is not a guarantee that if another observer is observing the same fluid motion from his reference frame, he will also get a steady velocity field. It's not guaranteed. So whether it's steady or not depends on reference frame. An example, imagine a boat which is moving slowly in a pond or a large lake, I would say, large lake, very large lake. Large lake. What I mean by large lake, what I want to show by saying this phrase large lake is that the boundaries of the lake are very, very far away from the boat. Okay, so the boundary conditions are not interfering with what is happening in the vicinity of the boat. So I have a boat here which is moving with velocity u, which is constant, as observed by this man, ground frame. Okay, so I am that person on ground frame. The boat is coming from that side and going like that. Now when the boat is very, very far away on my right, I look at the velocity field at this where the mic is. Okay, that is my x, and I see what is vxt. When the lake water is otherwise stagnant. Okay, only when the boat comes, fluid particles get disturbed. So when the boat is far away, the velocity field that the velocity that I will see at that location where the mic is will be 0, because otherwise the water is stagnant with respect to the ground. But as the boat approaches, that location will start experiencing the disturbance due to the boat, and you will start observing a non-zero velocity at that location as the boat comes towards that point. Does it make sense? Right? And thus Vxt, which is the velocity field observed by this man, is unsteady. At this time it's 0, but it's going to become non-zero as the boat approaches. Now consider the same fluid domain or the same fluid from the point of view of the man who is actually riding on the boat. So I have a new reference frame. The boat, it becomes the reference frame, and he is observing the fluid motion around him. Now the velocity field that he is going to be worried about, or what he observes, is going to be this symbolically. Okay, two things have changed from here to here. First, the frame has become B, it was G, it has become boat, ground, and he is going to have his own position vector. Every time you have a new reference frame, you get your own origin. You can't sit on this reference frame and use the origin of a different reference frame, right? So he uses this as the independent quantity. His position vector is being measured from here. Now imagine that now you are sitting on the boat and it is moving. If you focus your attention at a particular x prime, say 3 times I in front of you, you are the boat captain, you will see a non-zero velocity of the fluid particle, which is at 3I at this instant and also at the next instant. Imagine this. For you, the boat captain, whatever the fluid particle is at 3I ahead of you will have the same velocity at all the time. Do you agree? And right now I can only appeal to your imagination because we don't have the governing equations. Once we have the governing equations, and if you solve, you will get what I am trying to say. I am trying to make an attempt to invoke your imagination. So what is happening? Since for him the velocity never changes at 3I, whichever fluid particle is there, this is a steady velocity field. Okay, so this is an example which shows that whether a velocity field is steady or not depends on which reference frame, from which reference frame the motion of the same fluid particles being observed. Keep this in mind. I want to share something with you, how to do well on this exam, or how to do well on this course. Of course, there is the learning part, and if you are enjoying learning, it is very nice on its own. But at the end of the semester, you also want good grades. If you are willing to put efforts to earn good grade in this course, I want to tell you that you should read all my notes very, very carefully. When I speak, you may not be able to follow everything right away. I say this in every class to all my students. I am far from being a perfect communicator. I don't expect that whatever I am saying, you will grasp 100%. You grasp 30-40% what I am saying, that is fine. You go to your hostel room whenever you want to put time to this course, read my lecture notes very well. Because I will ask questions. Your MCQ questions I will make from this. When I make the MCQ questions, I make it for those students who have read my notes carefully. Yep. do that. Derivations, you do it once, at least once on your own, and solve the problem set questions. If you do all these sincerely and do not make silly mistakes on the exam, I think you will do well. Coming back, suppose we have a flow field and this with respect to a frame in context is 0 at all times and all locations. Okay. Choose a location L0 in the domain, a location, fixed location, and say, and we choose a time instant t0 right now. Draw a streak line using L0 and time t0. Draw a streak line. It may be something like this. Recall, the definition of streak line requires a location, choosing a location and a time. And then this will be the locus, streak line will be the locus of all those fluid particles which pass through L0 sometime in the past. Past with respect to current time instant. The streamline passing through L0 at instant t0 will coincide with the streak line. At this time instant t0, if you draw a streamline is always drawn at a given instant, and there will be several streamlines. If I choose a streamline that is passing through this location at this time instant, my claim is it will coincide with the streak line. If the velocity field is steady. Not only streamline will coincide with this, the path line of every fluid particle that is lying on the streak line. The path line of every fluid particle which is lying here will also coincide with this. Summarizing, what I am trying to say is, in a steady velocity field, streak lines, streamlines, path lines all coincide. Okay. Why do they do that? Why do they coincide? I am leaving this as a thought homework. Think and convince yourself. It's an exercise. People who have done the visualization experiment, how many of you have done? Last experiment number 8, visualization. Nobody has done. They are asking you to draw some of these things, streak line or path line or streamline. Now, at least for that experiment, you know what is supposed to be known early in the semester itself. Moving on. An Eulerian velocity field, when expressed in a coordinate system, may turn out to be what we call as one-dimensional, two-dimensional, or three-dimensional. More definitions. What I mean by one-dimensional velocity field when I am expressing this in a coordinate system. So here I am using Cartesian coordinate system. And if the velocity field turns out to be like this, I will say that it is one-dimensional. What I mean by one-dimensional is that it depends only on one of the three spatial coordinates. Note that ABC are constants, t is time. So the entire velocity field depends only on one of the three possible spatial coordinates. You see that? Only x2. This is an example of what I will call as a one-dimensional velocity field. Two-dimensional, only two of the three spatial coordinates appear. You see the example that I have made up. x3 is missing altogether. x1 is there, x2 is there. And that's why I call it two-dimensional velocity field. Three-dimensional is the general velocity field in which all three spatial coordinates will contribute. x1, x2 and x3. All right. More definitions. A velocity field, when expressed in a given coordinate system, can turn out to be one component field or two component field or a three component field. Earlier I talked about dimensionality. I am not now talking about component. An example of one component velocity field is this. One component means only one scalar component of the velocity vector is non-zero, other two are zero. In this example, the velocity field has only E2 component. And since it has only E2 component, I call it a one component field, one component velocity field. Okay, two component field, two components are non-zero. In that example, E2 is missing, E2 part is missing, E1 and E3 are non-zero. In general, three component field, all of them could be non-zero. I'll use this acronym later also in my lectures. C, when I say C, I'm talking about components. When I see D, I mean dimensionality. Example of a 1C 3D velocity field, I have written there. I hope all of you see why it is 1C, only along E1. Why it is 3D, all x1, x2, x3 are there. Okay. Keep in mind, for the same velocity field, when I say same velocity field, I mean the same vector field. Same velocity vector field is same, but then you can cast that vector in different working coordinate systems. If you choose Cartesian coordinate system, you will have E1, E2, E3 component. If you take the same velocity vector field and cast it in cylindrical polar coordinate system, you will have VR, V theta, Vz component, right? For the same velocity, the vector field, when the working coordinate system is changed, the dimensionality and what I am calling as componentiality, it's not a dictionary word, but I am sure it conveys what I am trying to convey. Dimensionality and componentiality may change if you change the working coordinate system. For example, have a look at this example. I have a velocity field. So first I have a Cartesian coordinate system. So there is a flow through a pipe. This is a pipe, there is water flowing through it. I have a frame fixed means pipe fixed or ground fixed Cartesian coordinate system. In that coordinate system, when I cast the velocity field, it turns out to be what I have written here. How it turns out, that's not important right now. But I'm telling you, it turns out to be like this, where A is a constant. Okay, R is big, R is the radius of the pipe. I am claiming it is 1C 2D. You agree? In the light of my definitions. In this form, it is 1C 2D. But if you change the working coordinate system and realize that x1 square plus x2 square is actually small r, the first coordinate of the cylindrical polar coordinate system, the velocity field starts looking like this. And what is E3 becomes Ez. What happens to componentiality still remains as 1C. In this example, some examples the componentiality also may change, but here the componentiality has been retained as 1C. What happened to dimensionality? Changed. Only small r is appearing. I will call this now as 1C 1D velocity field. Summary: componentiality, dimensionality depends on working coordinate system for the same velocity vector field. Two classes ago, I introduced you to the idea of a fluid particle. I hope all of you are comfortable with that idea now. As if it was not enough to give you the definition of a fluid particle, now I have a new definition of fluid element, different from fluid particle. What is a fluid element? So far we studied a fluid particle which is the smallest entity in continuum description. While the concept of a fluid particle is useful in understanding the translational aspect of fluid motion, it is not adequate to examine how the fluid deforms. In general, fluid deforms, it's non-rigid. Thus, we now need this idea of a fluid element. What do I mean by non-rigid behavior? Written there. Recall, rigid body was what? All interparticle distances remain unchanged. So non-rigidity means some or all interparticle distances may change. I want to examine that aspect. Not only I am interested in the motion of one fluid particle, that is at one level very useful to me, I also want to learn that if two fluid particles were d distance apart in this direction, in course of time, what happens to this distance, whether it increases or decreases. All right, that also I want to understand. And that is why I am bringing this idea. How it will be useful, we will see later, but this is the motivation. Now, a fluid element is a small piece of fluid comprised of numerous fluid particles. Fluid element के अंदर बहुत सारे fluid particles. The size of a fluid element is small but finite. It doesn't vanish. We don't want it to vanish. Want it to be small but not zero. Because zero होगा तो वो particle बन जाएगा. मुझे उससे कुछ ऊपर रखना है. I am saying the typical size of a fluid element would be this. If you visualize that as a cuboid, 10 to minus 3 meters each side. Is it bigger than fluid particle? You recall what was the dimension of a fluid particle on absolute scale? 10 to minus 4. तो मैंने इसको 10 गुना रखा उस in each size. So कम से कम 1000 fluid particles एक fluid element के अंदर है. An Fe has the same set of FPs at all times by definition. So an Fe is an identified set of FPs. Fe a fluid element, Fp fluid particle. Once an Fe has been identified with 1000 fluid particles, at all later times, the same 1000 fluid particles will be the members of this fluid element. Membership cannot change. And that will help us understand the non-rigid aspect of fluid. Now, understanding non-rigid behavior of fluid elements or fluid is important. At one level, it is just the curiosity. After all, how does it change? We know it changes, interparticle distances change, how they change. So I can pose the motivation at one level simply as my innocent curiosity. That is good. But it is not only the innocent curiosity why we examine fluid element. There are more concrete reasons. First is it will help in visualization how the fluid changes its shape, its volume while it undergoes motion. Okay, so a fluid element with its center of mass will translate, but at the same time how its shape changes. What was cuboid, whether it will remain a cuboid or will it become something else. It had some volume, whether it will retain its volume or whether it will expand or shrink. Those specific things we will be able to find out by doing this kind of analysis that is to follow. Further, experimental evidence shows that the internal forces that are developed inside a fluid, we represent them by stress. Okay. For example, in this solid, I put this force, and if I put this force, it will, and if it is static, if I'm supporting it, I put this force, you will say net external force is 0. But if I ask you what is the internal force, if I cut this imaginary cut and consider the left part, will there be some force acting on the left part because of the right part? In general, yes, right? And the same equal and opposite force will be acting on the right part because of the left part. So on whole, the internal forces don't matter, but if you take a part of it, internal forces matter. And it is important for an engineer to know the internal forces. Why? Why should we know what the internal forces are inside, say, this beam? If I'm using this to as a structure to hold some load, why it is important for me to know the force, say, at this cross section inside? Sorry? Yes, because all material have limit on how much load it can take. If it goes beyond that limit, it may crack. यहाँ से break हो जाएगा. That aspect we have to keep in mind. Solid mechanics course, you will do this in big way. In fluids also, we will do this. In fluids, the danger is not of breaking, because fluids as such doesn't break, right? But the importance of internal forces in fluids would be to actually get the governing equations. All right, and it turns out that experimental evidence shows that internal forces in a fluid depend on the rate of deformation of a small fluid element. Rate of deformation, rate with respect to time. So what I'm talking about is how much deformation happens per unit time. On that depends how much forces are being developed inside. This is the nature of fluid as we know it. Okay, so that is the second reason why we want to examine fluid element. Also, it turns out, again from experimental evidence, that it is not the absolute deformation that determines the internal forces, but not the absolute deformation, but the normalized, non-dimensional form of the deformation that matters. When you're talking about deformation rate, an appropriate normalized form of that actually decides the force. So we'll keep these in mind as we start our examination of a fluid element. So let's consider a flow field in which is being observed by this man here, reference frame F. He has a working coordinate system at his disposal to express various vectors, x1 Cartesian coordinate system, frame embedded, and here is a fluid element that he has identified for his analysis, a chunk of a piece of fluid. But since his working coordinate system is Cartesian, he has taken a cuboidal, this fluid element of this shape at t, at this time. Taking a cuboidal fluid element when the working coordinate system is Cartesian makes the analysis algebra simpler. If he had chosen cylindrical polar coordinate system, he would have taken a differently shaped fluid element. Both things will lead to the same results eventually. But for the time being, this is my fluid element. Now note that this fluid element has these edges which are parallel to E1, they are of delta x1, edges which are parallel to E2, that is delta x2, and the third set of edges are this long, small but not zero, small but finite. I call this fluid element A, B, C, D, E, F, G, H at time t. He observes this. At time t plus delta t, what will happen to this fluid element in general is what I have shown here. X was the position vector of vertex A, and that has become now x prime at t plus delta t. The vertex A has gone from x to x prime. Similarly, B, C, D, all other vertices have undergone some displacement. All vertices undergo displacement differently, and that's why what was cuboid at time t has no more remained a cuboid. It has become something else. That's a general figure. It has become something else than what it was. Few points I have, let me go over them. All vertices of fluid element are FPs. I hope it is clear. All vertices are actually individual FPs. Besides these 8 FPs, which are the vertices, every other point on the FE is an FP on its own. Those 1000 FPs that I talked about, they are all here. Okay. Each FP of the FE translates by its own velocity vector at time t, translates by its velocity vector at time t multiplied by delta t. This is how it will work, as simple as that. So why the cuboid has become something like that is because every vertex is having somewhat different velocity at time t than others. And every vertex will undergo displacement according to the simple formula local velocity multiplied by delta t. And if the local velocity at 8 vertices are different, that's the kind of thing you will get. Okay. That's what I have written here. Okay. So my analysis would be, or the kind of analysis I want to do is that AB was initially delta x1 away from each other. How far is B from A now? Will that give us an idea how non-rigid, about the non-rigid behavior of the fluid element? It was delta x1, AB distance. Now how much it is? May not be delta x1. Had it been a rigid body APL 100, we would have never worried about it. We know that वो delta x1 है तो वो हमेशा ही delta x1 रहेगा, अभी बदल जाएगा. So this is the kind of thing I want to look at. Now to be able to answer such questions, how far is AB or how far is AD compared to their initial distances, I need to track the coordinates of every fluid particle. Coordinate geometry से ही track होगा, right? So let's first identify the coordinates of vertices, all those 8 vertices at time t. I have written them here. Please check. I might have made mistake. So A is x1, x2, x3. That is the base location. And then I have written the coordinates of all other points. Let's scrutinize one by one. B is this, time t. Have I written correctly? Yeah, I'll put a tick. C, please check. Is it fine? D, ये लिखा है. Is it correct? x1, x3 same, x2 plus delta x2. Fine. E. Okay. F. Is it fine? H. G I have not written, but H, is H okay? Right. All right. So this is what at situation at time t. Now I want to know the locations at time t plus delta t. To find the locations at t plus delta t, I need to first know the velocity components, the local velocity components at the locations of those 8 vertices at time t. Velocity components of 8 vertices of Fe at time t. A is being treated as the base location, so I write that as V1, V2, V3. Somehow I know, and that is my base location. And then to write the velocity components, local velocity components at other vertices, I am using Taylor series approximation up to first order, using the location of Fp at A at time t and at this location as the base location. Now you please scrutinize whether I have written things correctly or not. Could be tricky because v1 also, the velocity components have to be chosen correctly, and then derivative has to be chosen correctly, and then delta xs should be chosen correctly. You have to pay attention to many things here. Very easy to make mistakes. I could have made mistakes yesterday when I was preparing the slides, and that's why I need your help to scrutinize. I am claiming that at point B, at time t, the three velocity components are this, using velocity at A as the base location. What do you think? I have written correctly or not? So there are three components. This is the one component, this is the two component, and this is the three component. Is this component okay? V1 plus del V, del V1, del X1, delta X1. Is it correct? Okay. Second one, V2. यहाँ 2 क्यों है? क्योंकि सेकंड कंपोनेंट वेलोसिटी की बात हो रही है, तो ये भी 2 होगा, ये भी 2 होगा. बेस लोकेशन की वैल्यू यहाँ आ गई, और फिर डेरिवेटिव लेना है not with 2 but with respect to 1, x1. Why? Because you are going from A to B, which is displaced along 1, right? So that's why 1. And the moment you get 1 here, it has to be delta x1. You can go back and check Taylor series. Then we come to the third component of velocity at B, base location v3. This has to be 3 because it's the third component of velocity. Again with respect to x1, because B is displaced from A, x by delta x1. And this is 1, this is 1. You understand this? Now based on this, you should be able to write velocity, 3 velocity components of all the 8 vertices, all the remaining 6 vertices. I have already written, you please scrutinize. I will not spend any more time. I hope you have understood how to write. Okay. So we know the velocity, local velocity. Now if you know the local velocity and the original coordinates of the F vertices, now I am ready to write coordinates of a vertex at time t plus delta t, as I said earlier, will be the coordinate of the vertex, that vertex at time t, plus local velocity component at time t at that vertex multiplied by delta t. That's the simple formulation. If you do that, we will be able to write the coordinates of vertices at t plus delta t. Vertex A, this is my claim. Please scrutinize. Is this correct? Okay. So mind you, A is not the origin. A was at x1, x2, x3. So it started with this value x1, and it can only change from x1. So that is why you are getting x1 here, x2 here, and x3 here. I am asking for the position vectors, coordinates of position vectors. So x1 plus v1 delta t, x2 plus v2 delta t, x3 plus v3 delta t. This is the new coordinates. These are the new coordinates of vertex A at time t plus delta t. So that is very simple. Let's work on this vertex B. My claim is these are the new coordinates of vertex B. I will give you half a minute to, or 1 minute to scrutinize, and if you have any, if I made any mistake, please let me know. Focus on this. Is it fine? Why have I put x1 plus delta x1 here? Because B was at x1 plus delta x1. So this is the original coordinate, initial coordinate of B, and then so much has been added to it according to the local velocity at B. Okay. Second one, x2 was the original location, not x2 plus delta x2 of B. So that's why I start only with x2, and then so much has been added. Similarly, x3 was the original location, so much has been added. Is everything okay? Acceptable? All right. So I am not going to write for all of them, but I will use some of them which I have not written. Onus is on you, responsibility is on you to make sure that what appears later, for example, for D, is completely in line with this understanding. Okay, in this way, we can track the location of all vertices at t plus delta t in terms of what? In terms of what? Either the velocity components at time t, or the derivatives of the various velocity components where at time t. Now here in this, on this slide or on the previous slide, I did not mention these things are at what time instant and at what location. I have not written because I do not have space on my slide. But I hope you know which time instant, ये derivative किस time instant पे है? T plus delta t? That's not right. Good that I asked this question. ये derivative किस time instant पे है? ये पूरी कहानी किस time instant पे लिखी जा रही है? T पे. T पे ही होगा. T plus delta t तो आया ही नहीं अभी. This is at t. And then the other question, at which location? Physical location, spatial location. किस spatial location पे है? Derivative किस spatial location पे है? Very good. It is at x1, x2, x3. Every derivative, because it's coming from Taylor series, right? तो टेलर सीरीज में सारे डेरिवेटिव्स कहाँ होते हैं? बेस लोकेशन पे. बेस लोकेशन मेरा ए पे है. एंड दीज एक्सपेंशंस आर बीइंग डन एट टाइम टी. इज इट क्लियर? Okay. So once we have tabulated all the coordinates in the background, now I come to the question of interest, quantifying rate of deformation of fluid element. The rate at which fluid element deforms can be examined in terms of rate at which its shape changes. मतलब ये एंगल जो 90 डिग्री था इस केस में दो एजेस के बीच में, will it remain 90 degree or will it change? It may change. At what rate it is changing? Shape, size of edges. AB was delta x1. Does it change with time? Yes, it changes. What rate it is changing? Okay. So what I'm trying to say is, when I say deform, I mean to quantify these changes, angle, their edge sizes, and the total volume. I want to quantify. The rate of fractional change, we will chase these quantities to understand rate of deformation. Rate of fractional change in the volume of the fluid element, we will define it like this. Vol means volume of the fluid element. T plus delta T at T plus delta T, and volume at T means the original time instant. We want to chase this fractional change in the volume. There is delta T in the denominator because, as I said, I want to chase rate of change, delta T going to 0. This is also called the dilatation rate. Dilatation rate. Is this word familiar? Dilate is this word. Have you heard this word before? What's the context? Yeah, expanding. People who wear specs, when you go for your eye examination, sometimes the eye doctor puts some drops in your eyes, asks you to wait for a couple of hours, and then he does some examination. Has anybody experienced this? I mean, it's a normal thing for an just normal test. It doesn't mean you have illness. You have experienced this? So the drops that he adds, If you ask the person why are you adding this, he will say that we want your, what is that called, iris, pupil. He wants the pupil to be dilated, such that, dilated means expand, the hole through which the light goes inside and hits your retina, he wants that to be dilated so that the eye doctor can easily go in and he can see the retina, how, if there is any problem. Same meaning, dilated. Dilated means change in volume. I want to look at that. I want to quantify that. Rate of fractional change in length of AB, which we will define as this. Length of AB, edge AB at time t plus delta t minus length of edge AB at t plus delta t and minus at t divided by the original length limiting value. Rate of fractional change in length AD, rate of fractional change in length E. I want to look at these things. AB, AD and AE. You can have a look at the length of fractional rates of change of other edges also, but this will be sufficient for us. From which point of view? From the point of view of being able to relate the forces that develop on a fluid element. These will be enough. I want to derive expressions for this, these. So this, in a way, this will answer what I wrote here, volume changes, edge length changes, and now I have to also quantify the shape, how it is changing. Now before I show you the quantities with which I will try to measure the rate of change of shape and all, I need to describe this figure, which is somewhat complicated. We will need this nonetheless. So this is the state of the fluid element at t plus delta t. Now what I am doing here in this figure is, I am taking projections of various points on various planes, starting with B. B is the projection of B on this plane. I am calling that as B prime. Right. So this was E1, E2, E3. I have three planes, E1, E2. I am oriented like this here. E1, E2, E3. This is my E1, E2 plane. Okay. E1, E3 plane and E2, E3 plane. I have three planes. Now those three planes remain the same, oriented in exactly the same manner at all time instants. Why is that so? Because the coordinate system is frame embedded and the observer is tied to the frame. So the plane's orientations do not change with time. However, AB, which was right now at time t, which was in this plane, 1-2 plane. AB was originally in 1-2 plane. AB was originally in 1-2 plane. At time t plus delta t, A has gone here. So A can still be thought as to be lying in E1, E2 plane. E1, E2 plane कह रहा हूँ मैं. X1, E1, X2, E2 plane नहीं कह रहा हूँ. A plane which is parallel to E1, E2 is also an E1, E2 plane. Okay, so A is here, but B has done something like this. पहले B ऐसे था, B ऐसे हो जाएगा generally. BA paper. I am taking the projection of this B on this plane. That's what is the point B prime. This is what B prime is. So projection on E1, E2 plane. So whenever I put a prime, single prime, it means it is the projection of the corresponding point B or D on E1, E2 plane. So B prime and D prime I am getting. And now the angles that they are making, who are making this AB prime and AD prime on that plane, or the projection of AB, the angle that AB prime and AD prime are making with E1 and E2 directions, I am calling them as delta alpha 3 and delta beta 3 angles. You have to pay a lot of attention to this. Okay, so this is 3 here, not very clear on that screen, but on your notes it will be very clear. Here also it is clear. This is delta alpha 3, delta beta 3, calling those angles. Also note that the direction of delta alpha 3 as being seen from here is counterclockwise, where the direction of delta beta 3 is clockwise by convention. The derivations that we are going to make, we will use this convention. But this convention is not a mandatory thing. If you don't want to follow this convention, want to say both angles should be counterclockwise, it is fine, but you will have your own derivations. Many places your derivations will differ from my with plus and minus, but not the final answer. So if you want to have this exploration with all angles counterclockwise, you are fine, you can do that. But all middle in between steps will be different. I want to stick to this. Delta alpha 3, delta beta 3, one counterclockwise, the other clockwise. Now then, double prime, whatever you are seeing, are the projections of the corresponding points on E2, E3 plane. All right. And the angles that those projections are making on E2, E3 plane, I denote them by delta alpha 1 and delta beta 1, as shown in the figure, and the directions as shown in the figure. Three primes will be projection of a point in E3, E1 plane, ye wala, sort of horizontal plane. And on that plane, the projections are making angles, delta, relevant projections are making angles delta beta 2 and delta alpha 2. Counterclockwise, clockwise, all shown there. Okay, now based on this picture, we would also like to look at or derive expressions for the following things. The projections of AB and AD on x1, E1, x2, E2 plane tend to align with each other. मतलब ये दोनों जो AB prime or AD prime है, rate at which they are collapsing towards each other. I want to quantify that, because that tells me that initially an angle which was 90 degree, at what rate it is departing from 90 degrees. That quantity is this. What will this be equal to in terms of velocity field? I will derive, but I want to chase this quantity. I also want to look at rate at which the projections of AD and AE on x2, x3 plane tend to align with each other, and that will be delta alpha 1 and delta beta 1. मतलब ये वाला projection और ये एक दूसरे पे किस rate से अब एक दूसरे की तरफ जा रहा है. That is my interest to know. And finally, the rate at which the projections of AE and AB on 1,3 plane tend to align with each other, I want to know that, and that is quantified as delta alpha 2, delta beta 2 added divided by delta t. Okay, this will tell me initially the angles which were 90 degree, at what rate they depart from 90 degree. Okay, so I have 7 quantities in front of me on the slides, which I believe will tell me the rate of deformation of a fluid element, and later it will help me quantify the forces. The next thing on our agenda is to find their expressions in terms of the local velocity field V1, V2, V3, or the derivatives. We will do that this afternoon.